Hello student, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today's topic is about the Maxwell equation on the subject of electromagnetic wave. In this lecture, I am going to give the lecture about the Maxwell's equation, the four different kind of Maxwell equation. I am going to prove all those equations and of the differential form and the integral form. So let's begin with the class. Contents of this lecture is the introductions of basic laws of electromagnetic induction, Gauss's law for electric fields, Gauss's law for magnetic fields, Faraday's law, and the Ampere-Maxwell law. And we will going to conclude through Faraday's law and Ampere's-Maxwell law using the Biot-Savart law and the Ampere-Circuit law. And using all those basic laws, we are going to describe the Maxwell equation. We are going to prove the Maxwell equation through these contents. Okay, so let's begin with the class. So introduction is that in Maxwell's equation there are the electrostatic field produced by the electric charge, the induced field produced by the changing magnetic field. So do not confuse the magnetic field with density magnetic B, this is the magnetic flux density, and P is equal to mu H, where the B is the magnetic flux density, which is equal to the permeability of the medium, and H is the magnetic field strength, and H and the B the induction magnetic flux density. The unit of magnetic flux density is Tesla. Mu is the permeability of the space, and H is the magnetic field strength, and the unit of it is A by meter, or you can use it Weber per meter square, or you can say it as a Tesla. Tesla for B, and H is for the ampere per meter. Okay, so let's go to the next slide. The Gauss's law for electric field. The Gauss's law for electric field is that the electric charge produces an electric field, and the flux of that field passing through any closed surface. Electric charge produces an electric field, and the flux of that field passing through any closed surface is proportional to the total charge contained within that surface. Or if we have to describe in a proper manner, is that suppose there is a total amount of electric displacement vector that is coming out of that surface is equal to the net charge enclosed by that surface. Suppose there is a surface a specific amount of charge which is enclosed within that surface is equal to the total displacement vector that is coming out of that surface. So the integral form has been written here, and the differential form is also written here. Okay, so let's go to the next slide. And this is the Gauss's law for electric field. So this E is the, reminder that this electric field is a vector field. Okay, the dot product tells you to find that part of E parallel to N perpendicular to the surface, the unit vector normal to the surface, Q the amount of change in coulombs, reminder that only the enclosed charge contributes, epsilon 0 is the electric permittivity of the space, and an increment of surface area in meter square, the electric field in Newton per coulomb, and the reminder that this is a surface integral, not a volume or line integral. So let's go to the next slide. The Gauss's law for electric fields is a differential form. It is del cross H, which is equal to del dot E, which is the divergence of electric field, which is equal to rho by epsilon 0. Rho is the surface, the volume charge density, and epsilon 0 is the permeability of the free space. And this is the the del operator that is working on the electric field. So this is the first differential form, where we can say the divergence of electric field is equal to the volume charge density that is enclosed by that loop. So let's go to the next slide. Gauss's law for magnetic field. Now Gauss's law for magnetic field integral form is that del dot B is equal to 0. This is you can use that del dot H or del dot B, because B is equal to mu 0 H. We have already know that magnetic flux density is equal to the permeability of the space of the medium into the magnetic field strength, which is equal to 0. So we can write that divergence of magnetic flux density is 0. and here the total magnetic flux passing through the any closed surface is 0. Now if we have to describe it, we have already described in the class that suppose there is a certain amount of magnetic charge that is enclosed within a surface. Now we have already know that of magnetic charge is always in a two form. One is a plus and one is a minus. So total charge that is enclosed within the surface will be 0. So that's why if we take a divergence of the magnetic flux density or magnetic field strength, it will always equal to 0. So that's why the second differential form equation of Maxwell equation is del dot H or del dot B is equal to 0 for differential form, and for integral form it will also be different. So let's go to the next slide. So Gauss's law for magnetic field is integral form. Is that the reminder that the magnetic field is a vector? We have already know that. Dot product tells you to find that part of B parallel to an n perpendicular to the surface, the unit vector normal to the surface, and increment in the surface area in meter square, the magnetic field induction in Teslas. Reminder that this integral is over a closed surface. Reminder that this is a surface integral, not a volume or line integral. The Gauss's law for magnetic field, that is a differential form. Magnetic field is a vector. Same here. Okay, so del dot H is equal to 0. We have already described it, how it works. So if a divergence of a magnetic field strength or magnetic flux density, it will be equal to 0. Okay, so let's go to the next slide. And this is the Faraday's law. So as you can understand, what is the Faraday's law is saying? The Faraday's law of electromagnetic induction is saying that total EMF around a closed loop is equal to the rate of change of the magnetic flux enclosed by that loop, and the direction of the EMF is such that the magnetic field produced by this current, because of the EMF, opposes the original magnetic field. That's why we can say that the EMF is equal to the contour integral of E dot dl, and E dot dl is the electric field strength or electric field, that is also a vector quantity. Now the contour integral or closed path integral of E dot dl will be equal to the minus del phi del t, and that phi is equal to the total magnetic flux. We can say the total flux enclosed by that loop is phi. Now that phi can be written as the surface integral of B dot dA. Now what is the B dot dA? B is the magnetic flux density. Now and the dA is the infinitesimal small area of that closed path. Now within that closed path, suppose the area of the closed path is a big A. Now dA is the infinitesimal small area in that closed path. Now if we take a surface integral of B dot, if we take a surface integral of the dot product of the magnetic flux density and the infinitesimal small area, we will get the total flux of that enclosed surface. Now what does that mean? That contour integral of E dot dl is equal to the minus del of del t of that surface integral. Means the total change of the magnetic flux density will be equal to the E dot dl, the closed contour integral. So E dot dl is representing as the total EMF around the closed loop. So that's why we have taken the path integral, closed path integral of E dot dl, and it will be equal to the rate of change. To show the rate of change, we have used the del of del t, which will be equal rate of change of magnetic flux enclosed by the closed loop, and total enclosed flux in that surface will be surface integral of B dot dl. Now using the time varying field, we will explain that del cross H, the curl of electric field, will be equal to the minus del B by del T. Now it means the curl of electric field intensity, electric field strength, will be equal to the rate of change of magnetic flux of that particular area. Let's go to the next slide. Now this is the Faraday's law. Is the integral form of Faraday's law will be saying that closed integral of E dot dl is equal to the minus surface integral del of del t of B dot dl. So that is the Faraday's law. Let's go to the next slide. And this is the differential form. This is the differential form, the point solution that we have already showing in this slide, that del cross E is equal to minus del V by del T. Okay. So we have already described how it works. So let's go to the next slide. Now the Ampere-Maxwell law is the integral form, is saying that the differential form is saying that del cross H is equal to the J plus del D by del D by del T. Now we have to explain what is the del D. Now del D has been written as epsilon into E. Now D is the displacement vector and it will be equal to epsilon into E, that has been showing here. It is the epsilon 0, and epsilon 0 is the dielectric constant of the free space, and E is the electric field strength. Now D is equal to epsilon 0 into E. So if we take a if we have a time varying field, then the curl of the magnetic field strength will be equal to the conduction current density plus the rate of change of the displacement vector, and the displacement vector can be written as epsilon 0 into E, where the epsilon 0 is the dielectric constant of free space. Now epsilon 0 can be we can, as it is a constant, so we will not apply the differential operator on epsilon 0. So epsilon 0 will be we will put it here, and we will operate on the electric field intensity. So that's why it is been written as J plus epsilon 0 into del of del T of E. E is the magnetic electric field intensity or electric field. Okay, so let's go to the next slide. Now the Ampere, this is the Ampere-Maxwell law. It's the integral form that has been written here. We have already described how it works. That suppose the closed path integral of H dot dl. Now H is the magnetic field strength, and dl is the total path which is enclose the surface. Now dot dl is the infinitesimal small length of that specific path. So if we take a closed contour integral of dot product of magnetic field intensity and of infinitesimal small length, then we will get we will get another equation that will be equal to the surface integral of J plus del D by del T dot dA, and J here is the conduction current density that can be written as this I can be written as J into conductivity, that can be written as mho. So it can be also written as J plus del D by del T dot dA. So if we take a dot product of total conduction current density and the displacement current density, now J is the conduction current density and the D is the displacement current density. Now if we take a dot product of infinitesimal small area and the J plus del T by del T, then we will get the closed path of H dot dA, and that is the Ampere-Maxwell laws integral form. And this is the differential form. This we have already described that. Now if we take a if we just by using the Stokes theorem, we can prove that del cross H, it means the curl of the magnetic field strength will be equal to the J plus epsilon 0 into del E by del T. Now J is the conduction current density and epsilon 0 is the dielectric constant of the free space, and del E by del T is the time, it shows the time varying field, where it shows the rate of change of electric field strength by electric field intensity. So this is the equation. So this is so as we can see here from that Maxwell equation has four different equations. One is for differential form. The first that is been extracted from the Gauss's law. In case of Gauss's law, we know that del dot D is equal to rho V. It means divergence of displacement vector is equal to the volume charge density of the surface that has enclosed the total volume. So and the integral form of that specific equation can be written as the surface integral of D dot dA. D is the displacement vector, and dot product of displacement vector and the infinitesimal small area will give you the total charge that has been getting out, total displacement coming out of the closed surface. So total displacement coming out of the closed surface can be written as surface integral of D dot dA. Now because D is the total displacement vector. Now if we take a closed surface integral of displacement vector on an infinitesimal small area, now if we take a surface integral, what we will get? We will get the total displacement vector that is coming out of the net enclosed surface, and that will be equal to the total net charge enclosed by that closed surface. Now if we have a closed surface, now if we take rho V as a volume charge density. Now if we take a volume integral of that volume charge density, what we will get? We will get the total charge that is enclosed by this closed surface. So Gauss's law is saying that total displacement coming out of a closed surface is equal to the net charge enclosed by that closed surface. So it is equal. So as total displacement coming out of a closed surface is equal to the net charge enclosed by this closed surface, we can written it as a way in an integral form, that surface integral of d dot dA, where d is basically d is equal to epsilon into E, where epsilon is the dielectric constant of the medium, E is the electric field strength. So we can written it as a d, and the dot product of d and dA will provide you the total displacement vector that is coming out of the surface that has been enclosed by a specific path, and it will always be normal to the surface. Now that will be equal to, according to the Gauss's law, to the net charge enclosed by this closed surface. Now if we take rho v as the volume charge density, and if we take a volume integral of that volume charge density over the surface, what we will get? We will get the total enclosed charge that has been bounded by the surface. So it will provide you the integral form and the differential form for the Gauss's law. Now if we take the second law of Maxwell equation, that has been written as del dot B is equal to 0 for differential form, and for integral form it has been written as surface integral of B dot dA is equal to 0. Now the same thing, we have taken the same surface where the dA is providing us the infinitesimal small area of that enclosed surface. Now if we take a surface integral of that magnetic flux density, where the B is denoting as the magnetic flux density, and also it is a vector. So taking a surface integral of B dot dA, or taking a surface integral of dot product of B and dA, will provide us a zero value. Why? Because if you take a magnetic field which has been enclosed within that surface, it will be provided us with a net charge of net zero magnetic charge. Why? Because as we know that a magnetic charge always contain a positive pole and a negative pole. So suppose there we have 20 or 40 positive pole, and the same thing, and a very close proximity, there will be the same amount of negative pole that will be present in that enclosed surface. So if we take a surface integral of dot product of magnetic flux density and the infinitesimal small area, it will provide us a zero value, and that will be indicated in the integral form, where we have written here that surface integral of dot product of B and dA, where dA is the infinitesimal small area, is equal to 0. And the same thing, if we take the divergence theorem, if we use the divergence theorem, using the divergence theorem, we will provided us with a differential form equation, where it has been written here that divergence of the magnetic flux density, which is also a vector, will be equal to 0. Okay, so this is the second Maxwell equation, and now we are going to understand the third Maxwell equation. Third Maxwell equation has been written as, in differential form, is del cross E is equal to minus del B by del T, and in integral form it has been written as a closed path integral of E dot dl, which is equal to the rate of change of the surface integral of dot product of B dot dA. Now if we have to prove it, we have to know what is the Ampere circuit law. The Ampere circuit law is saying the magnetomotive force around a closed loop is equal to total current enclosed by that loop. So as we have know that magnetomotive force will be what? Is the closed integral of the H dot dl, which will be equal to I. Now I is nothing but the surface integral of conduction current density over an infinitesimal small area. Now if we take a surface integral of dot product of J dot dA, we will get the total current enclosed by that surface, and that will be equal to the closed path of H dot dl. Now using the Stokes theorem, we will get del cross H is equal to del cross H is equal to J. It means the curl of a magnetic field strength will be equal to the total conduction current density. But as we can see, we will have a postulates problem. Now if we put del cross H is equal to J, and from the rate of change of charge, we have know that net outward current, which is equal to J dot product of J dot surface integral of dot product of J and dA. We will have that J dot surface integral of J dot dA will be equal to minus del of del T of total volume charge density, and it will provide us with the equation that will say that divergence of a conduction current density will be equal to the rate of change of volume charge density, which is written as del dot J is equal to minus del rho V by del T, and which is also known as continuity equation. So it will provide us a discontinuity. So from that we will describe a conduction current density and a displacement current density, using which we can write that del cross H is equal to J plus del D by del T in a differential form. And in integral form it can be written as closed path integral of H dot dl will be equal to surface integral of J plus del D by del T of dot product of J plus del D by del T and dA. So this is the integral form, and from the Faraday's law we can write we can write the total EMF around the closed loop is equal to the rate of change of magnetic flux enclosed by that loop. So it can be written as del cross E, the curl of electric field intensity, will be equal to the rate of change of magnetic flux density, and it can also be written as an integral form here as the closed path integral of E dot dl, the dot product of electric field and the infinitesimal small length, will be equal to the surface integral of rate of change of total magnetic flux, that can be written as dot product of B dot dA. So this is the differential form and that is the integral form, and using the differential form we can get a point solution of any medium. So if the medium is continuous, then we will use the differential form equations, and if we have an integral form which can be used in a discontinuous medium, it means if the medium is not homogeneous, the parameters are different, the value of the electric field and magnetic flux density are different in different point of a free space, we will use the integral form. If the medium is continuous, where the d, e, displacement vector, b as a magnetic flux density, magnetic field strength, conduction current density, all these parameters are constant throughout the space, we will use the differential form, because using differential form we can extract a point solution. But in case of integral form, if the medium is discontinuous, where the J, the value of conduction current density, displacement vector and the magnetic flux density is different, we will use the integral form. By using the integral form we will get the different value at different point, and then we integrate it, and we can find the boundary condition at media interface. So these are the Maxwell equation, and for the next lecture we are going to describe the boundary condition. And as we can see that we have described the point solution, the point solution and the continuous solution, point solution, the boundary condition and media interface. In case of point solution we use differential form. In case of boundary condition, to define or find the boundary condition at media interface, we will use the integral form of the Maxwell equation. So we will conclude our lecture here, and we will continue with the boundary condition of the Maxwell's equation in different media from the upcoming lecture. Okay, thank you.